So this is the first talk of today by Robert Stump from University of Manitoba. And he will talk about level attraction and exceptional points in cavity magnonics. So Robert.
Okay, well, thank you. And first, let me begin by thanking the organizers for allowing me to present and participate in this meeting. It's a bit different from what I'm normally presenting in that I'm a physicist. And my colleague here, I think I can show a laser pointer. My colleagues and I, and especially Igor Proskurin, this is the work which I'll be presenting. Igor is a research associate and Jefta is a PhD student. And this is kind of a combination. Igor is more the mathematician and I'm more the physicist. So say that up front. And I'm going to present the talk primarily from a struggle I've had for the last 4 years, or we've had, trying to understand some experimental results. So I'll explain that story as we go along. And this is an update at where we stand at the moment, which I think we've made some progress, but there's still ways to go. First, though, let me just explain the full backstory. I arrived here at this university about 4 years ago. I discovered I was in roughly the geometrical center of the North American continent. And it has very beautiful summers, as you can see. It also has very cold winters. But the main point of this slide is that I'm here because there's quite a lot of research, experimental and theoretical, in the dynamics of magnetism. And that's what this talk is about. It's a special kind of dynamics. And when I arrived 4 years ago, there were some experimental results from this laboratory on cavity magnonics, which just seemed completely strange to me. I did not understand them at all, and I'm still not sure that we understand them very well. So that's where the story is going. And where I'll begin, however, is a little bit in a different spot. It's a model which we've come across, which gives, I think, the essentials not only of the mathematics, but of a lot of the physics, which both of which we're trying to put together in a nice way. And this plot is the puzzle point. This is frequency on this axis and some another driving frequency parameter on this axis. And these are two modes which coalesce at these 2 points here called exceptional points. And in between is a region of instability. So, and these are we're talking about electromagnetic excitations because these experiments are typically done in some sort of attuned cavity. Now, to put this in perspective, let me give you the simplest possible model that we've come across. It's, again, has an experimental component, but it has also a very nice generic mathematical model, which seems to describe what is observed. So the physical model is really a very simple electrical circuit. This is a very small microcapacitor, but the capacitor has a plate which can move, so the capacitance can vary. And it is coupled inductively to a driving field, which in this case is designed to be in the microwave frequency range. And this is a tuned circuit. But it's a tuned circuit in that this capacitance can vary, so the frequency can vary. And this is a mechanical part. And this is the electric model. And it's a one model of, say, a mechanical system where there's an optical cavity. And these A daggers are some operators which create photons inside this cavity with a frequency omega and a damping rate kappa. And there's a fixed mirror and this is the pump, this is the drive, the laser. And the other mirror is on a flex. So it can move, and that's what's mimicked here by the capacitance. And the flexure itself has its own resonant frequency and its own damping rate. And one then varies the driving frequency. And part of the story, which I'll be talking about later, is what do these damping rates, how do they have to match in order to see the sort of picture I showed you in the previous slide with this mode attraction. So let me go on with a simpler model. And depending how you drive it, there are two results. The result on the left is the one I'm most familiar with. This is the one that doesn't surprise me. I've spent most of my career studying similar sorts of things. There's a cavity mode here at a fixed frequency. This is frequency, but it's a detuning parameter. And this is a cavity mode, and this is the mechanical mode. And when they start to overlap and there's interaction, then they repel. And so you get a nice branch up here and a nice branch down there. And this is the detuning parameter I mentioned before. It's the measure of the driving field difference from the tuned resonant resonance of the cavity or the mechanical oscillator. This picture on the right is the one that puzzles us. And in this case, you're driving it in a different way at a different frequency range. And instead of seeing modes repel, they collapse together. And in between seems to be a region of instability. Now, the way you drive it is if you drive above the cavity frequency, there's this mode attraction where you have an excess of high frequency photons. If you drive it below, you see the mode repulsion. And the way that we can understand this in a sort of a hand-waving picture is that if we go into the rotating frame of the drive field, then when you are driving it in one way, the cavity mode is negative. And so in that sense, it appears that one gets this sort of attraction. So another way of looking at it is this kind of a picture I'll get to in a moment. So let me explain the model. It's a generic model where you take these steps. So here's the cavity gas of photons, and these A-dagger-A are the number operators which are counting the number of photons in this system. And it's an open system. So, and we're driving it, and this is the cavity frequency. And then we also have the mechanical mirror, which is another set of bosons, and we have a different number of bosons in the mechanical system, and they have their own resonant frequency. And the Hamiltonian, the total Hamiltonian for this optomechanical system then is all of the energy in the cavity system of photons and all of the energy in the mechanical system of bosons and some interaction term. Now, the force, the way of getting equations of motion and solving for the allowed modes that one can observe, in this case, is coming from this flexure. Now, by flexing it, you're changing slightly the dimensions of the cavity. You're shifting the frequency of the photons. So if we expand the cavity frequency out and take just the first order term, which is proportional to the degree at which you've deformed the mechanical mode, then this is a perturbation onto the energy of the cavity. And we can then, and that's coupled then, this X is then is a measure of the degree of freedom in the mechanical mode. And so we have a coupling term immediately just by taking this first order term, and that's put into this coupling constant, if you will, G0, which contains the shift in the frequency. And that gives us our interaction, which then, this is the generic part of the model in this kind of approach. First, we take the Hamiltonian, we switch to the rotating wave approximation, then we linearize it to lowest order terms. And that means that the interaction term then has something which is proportional to the number of photons in the cavity times these interaction terms, which represent the creation and destruction of photons and the creation and destruction of bosons inside the mechanical mode. And that's the generic model, and it's parameterized in terms of the difference between the driving field and the cavity frequency, and as viewed from the rotating frame of reference. So that's our generic model. And this is where we get this nice interpretation that depending on whether you're driving above or below the resonant frequency, either you're pumping energy into a stable mode, which in this case is just like a simple harmonic oscillator. It's a pendulum oscillating back and forth with some characteristic frequency. You're coupling into that, and then we see mode repulsion. However, if instead we are coupling to the unstable mode, we are effectively driving an inverted pendulum. And so and you're looking at small fluctuations around that driven inverted pendulum, which is of course unstable. And that is the basic content of this simple generic model. And so putting it this way, we see then when we are driving this unstable mode, there's a region of instability. There are these 2 points where modes collapse. And in fact, these are interesting points if you go around them. And some people can do this in experiment. They can vary parameters and try to circle around this point. And you see a change in phase of the wave that the excitations you're coupling to, and it's a different phase change over here. And they have different intensity amplitudes as well, because the unstable peak and the stable peak are not equivalent in that sense. Now, here's the catch. The catch is in this model, I haven't put anything in about explicitly energy that's lost outside these two coupled oscillators, even though we're driving it. In the experiments, the ones we're aware of, in this particular experiment with the mechanical mode, the attraction was achieved by adjusting the damping rate of the mechanical oscillator with an auxiliary field. So you had to adjust that just the right way. Then you could see this attraction. And this is going to come back when I talk about the magnetic system in a few slides. So now, let me talk about the magnetic system. That was a model. And it's a generic model, and we can explain, I can show you now how we explain dynamics in a magnetic spin system, particular type of magnetic system, with the very same model. But first, you may not be too familiar, not all of you will be familiar with the dynamics in a magnetic spin system, so let me spend a little bit on this slide to explain that. What I mean by magnetic spin system is if I say I've got a ferromagnet, the kind of thing you hold messages to your refrigerator door with, the electronic spins in these materials order in such a way that the spin prefers to be parallel. That's what's represented here by these red arrows. But the dynamic of these, because they are actually spin angular momentum, means that the dynamics, if I think of it classically, is described by a torque equation. So if M represents the average magnetization or the local magnetization even of any of these individual spins, then the corresponding time rate of change is given by a cross product with some effective field. And if and this is the conservative dynamic part, so just M cross this effective field E effective, and H can contain interactions with the other spins as well. So this is the conservative part. But if I include also dissipation, one of the standard models, which works really well in many cases, contains a term which is M cross dm T. And the dynamics then is this: if there were no dissipation, there would just be a nice steady precession like that. So that's a precession here around some sort of stationary axis. And if you look at the precession from the top, then you would see these rotating spins like that, or that projection of the spins. If you include this dissipation term, then there's a gradual decay back to this orientation of this field H effective for each of the individual spins. So that's, in a nutshell, the precessional dynamics, and the dissipative term appears down here. Now I'm going to be concentrating for the most part in the next few slides just on this part, the conservative term. Now, if we want to make a direct connection as close as possible to this mechanical oscillator with a magnetic spin system, you might wonder how in the world you do that. Well, there's one other thing that magnetic spins do. And you'd use this for data storage all the time in a magnetic hard drive. The information in a magnetic hard drive in a bit would be contained by the direction of these little arrows. And if you want a bit 1 or a bit 0, you'd point them in opposite directions. Well, to do that for a continuous chain of ferromagnetic spins, you have to put in a kink. Well, that kink actually, if you take the torque equations, the classical ones, and you include a nonlinear term which describes a preference for which way these spins point. This term describes a preference for the spins to point next to one another. This term just describes, well, I want to point to the left, or I want to point to the right. I don't care which, but I want to point one of those directions. Then if you put a twist in, these compete. And they compete in such a way that it forms a soliton-like shape. A topological soliton, given by this profile here, has a very well-defined characteristic width, which is just a ratio of these two terms. And this object then moves without changing its shape. And if you create a pinning potential, a well where it likes to sit, with where the kink has its highest kink, it likes to sit in the middle of this well, then we have everything we need for a harmonic oscillator. This maps directly onto the mechanical motion that I described earlier. And in fact, we can construct the Lagrangian and equations of motion for this. There's a pinning potential, which tells you where it likes to locate. The precessional term introduces the inertial effect. And so then we get a Hamiltonian, which looks just like a classical Hamiltonian of a mechanical oscillator, which is exactly the same sort of Hamiltonian we were using to describe the optomechanical problem I showed you at the very beginning. So we have everything we need, except one thing. We need an interaction term. So what we choose for the interaction term is a phenomenological description of something which does occur. People use it to use light to change the direction of spins. It's called the inverse Faraday effect. And what it means is that you get an effective magnetic field for the electric part of an electromagnetic wave, which then gives you the second order term, coupling to the left circular polarized photons and the right circular polarized photons, but with a competition between them through this minus sign. So when we do this, we get the equivalent of our optomechanical interaction term for the magnetic domain wall, this soliton kink, with this, some coupling constant, effectively something which plays the same role as this displacement, which is the number, basically the number of excitations in the mechanical part, and the energy of the optical mode. And we've got the kinetic energy associated with this magnetic domain wall. So this effective magnetic field applies a pressure to the magnetic domain wall, causing it to oscillate in its pinned potential, and the restoring force then given by the shape of that pinned potential. And this is exactly the same dynamics in a completely different system, a magnetic spin system. What we see here is, depending on how we drive it, we get exactly the same behavior. We can, in this simple theory, we can then do the same thing we did before, switch to a rotating frame of reference, linearize, we get the interaction term, which now depends on the right and left circularly polarized photon gas, the occupation numbers. If we drive it one way, we get mode repulsion. If we drive it another way, we get mode attraction. Now, one thing I'll point out here is in a real experiment, it might be hard to envision just one single domain wall. Now, there are other materials which have an interesting property all by themselves. They have a chiral symmetry breaking interaction, which means that the spins don't order parallel to one another, but as you go down an axis, they rotate in a chiral way, and it's a well-defined chirality, and it's determined by the nature of this interaction. And this would be such a chiral lattice. If you apply magnetic field, it does an interesting thing. It's a single crystal, and if you apply magnetic field, you favor one direction for the spins, but because this competes with the chiral interaction, what happens is you get kinks here, another type of soliton, chiral soliton lattice is what they're called, where you can adjust the spacing between these chiral solitons by applied magnetic field. These are very interesting materials. They're low temperature, but they belong to a class of materials where you can also, in different situations, see things called two-dimensional solitons, which are quite the rage now, called skyrmions. And anyway, we can see the same sort of dynamic for this chiral, or we believe you can see the same sort of dynamic for this chiral soliton lattice. That was the picture I showed you earlier, where if you drive it in the right way, you see a chirality dependent driving. In one particular way, you can see mode collapse like this, which, by the way, just as an aside, if we pick another more complicated multi-sublattice magnet, where spins point opposite one another, this is an antiferromagnet, it can have a magnetic domain wall as well. And we can put explicitly this symmetry breaking chiral interaction, which looks like a S cross S term, into that. Then we have the same thing we had before, ferromagnet with this soliton-like twist. However, this chiral symmetry breaking interaction distorts the wall. And these are of interest for applications. People study these, and one of the things they can't do is figure out what the strength of the interaction is. And so we can show then that if we follow that same theory, looking at a domain wall, but in this two sublattice system and including the symmetry breaking interaction, then in a particular way, we can get a very, very clear dependence where there's either a repulsion gap or an attraction gap, which is directly proportional to the magnitude of this symmetry breaking interaction. So that in a real experiment, that might be an application. You could actually extract that number if you were able to do it. Now, with all of that, what I've done is first talk about a simple generic model for a mechanical oscillator coupled to an electromagnetic oscillator, this photon gas, shown that you can see mode repulsion, mode attraction, depending how you're driving it. It's something where we use a rotating wave approximation and then an interaction which introduces some nonlinearities, which we then linearize, and we retain then this interaction, which gives us the dynamic we're looking for. Now, we realize that in terms of magnetic systems, but in a very special, particular way. That isn't what started all of this work 4 years ago. What started this work all 4 years ago was not a complicated magnetic domain wall spin texture. It was something much simpler. It was a ferromagnet. It was the magnet that holds notes to your refrigerator. Because I went there, and 4 years ago, I saw this picture from the lab on such a magnet, and then they showed me this picture, and I didn't understand that, and we're still not sure we understand how they got this mode attraction, because there was no evidence from their experiments that nonlinearities were playing a role. So let me back up and show and take you now through our thought processes and what we learned in trying to understand it. On the one hand, we learned that yes, we can make magnetic analogies, but nonlinearity is essential. Dissipation, well, none of the models I showed you before relied on any kind of dissipation for the magnetic system. Here, let's look at it from a different point of view. If we know that the photons classically can be described by Maxwell's equations, and Maxwell's equations are equations of motion for the electric field, which couple to the magnetic field, and the magnetic field, which couple to the electric field. We can get equations which describe then propagation of light. If we want to talk about propagation of light inside a material, we include a constitutive relationship, which basically says, well, there's a permeability, which describes then, there we go, a magnetization through a linear response function if you drive it with a magnetic field. There's a permittivity, which would do the same thing, but for the electric field. We're not going to pay much attention to that. And the cavity experiment we want to describe is something between essentially two mirrors. It's in microwave frequency, and there's a spin which precesses inside. That's our system. Now, if we take Maxwell's equations, we say that there's a small perturbation to the electric and magnetic fields associated with the presence of this material inside. Then we get the Maxwell equations with two terms that couple to this perturbation of the permittivity, which we're not going to pay attention to, but the magnetic side we'll pay attention to, and that gives us something which looks like the time derivative of the perturbing magnetic material. And so this is then the coupling term to Maxwell's equations. What we learned there immediately was in linear response, we only see mode repulsion. And that's hence the basis for my confusion, because this is how I understand all of these experiments have going on. When we look at the experiment, however, they seem to also be able to see, by driving it in the right way, this mode attraction. And the question is why? Now we could come up using our simple model, exactly this generic model I showed you before, and we can describe this system, but only if we include an additional oscillator that allows us to drive it with a diamagnetic coupling, which means a negative of this term I showed you up here. If we can change the sign on that, everything's fine. One sign we get low level attraction, one sign we see level repulsion. This wasn't really satisfactory. We didn't have a physical explanation for it. Some more recently, this group that made these measurements have proposed that yes, there is an additional contribution which involves the photons in this system, which are acting basically as a dissipative coupling mechanism. So I mentioned that earlier with an optomechanical case. You have to match the dissipation rates in just the right way to see mode attraction. This may be the story. I don't know. I don't know the experimental proof for that, but they've come up with some nice experiments which seem to suggest it's the way. But we came up with some other things. We learned something which is really interesting, we thought. This is more recent. What we did was look back at a paper. It was about 20 years ago, in fact. And this paper talked about the dynamics of precession, of a single spin. You remember I showed you back in this slide, the dynamics of magnetization is precession about some fixed direction. Well, the precession angle, as it gets larger and larger, we normally associate with very high degree of nonlinearity. It is quite a nonlinear set of equations. They're inherently nonlinear. Magnetic systems, for that reason, have been used for decades as models of nonlinear dynamics. You can drive it with high power microwave fields and see all sorts of things, from bifurcation and lower order bistable modes, all sorts of things. But a single spin precessing, which has azimuthal symmetry, is special because it just precesses in a nice circular way without any oscillations, no elliptical precession, which oscillates in this direction. Now, what this paper showed is that if you have this symmetry, one of the things it showed is if you have this symmetry, you can have small fluctuations about a stable precessional trajectory. However, there's another solution. There's a solution which is an unstable stationary trajectory, and fluctuations about that lead to collapse and instabilities. So we had the basic ingredients just in these torque equation dynamics for exactly what we were seeing with the optomechanical and rather complicated interaction term. So we explored this. And indeed, we see that with this symmetry, the precessional angle can be quite large, and it's still precessing around in a stationary trajectory. There's two possibilities in this high symmetry case, and they're called P modes. One of them is stable to small fluctuations about that orbit, and one is unstable to those. And so the property is we suppress this symmetry suppresses the nonlinear higher harmonics. There are two excitations, and the phenomena of mode repulsion is when you drive the stable mode, and mode attraction when you drive the unstable mode. The problem now is, how do we come up with a model that can capture all of that? And the model, and we'd like, moreover, we'd like this model, we're looking at large angle precession, and when we go beyond systems which have that simple symmetry, it becomes rather difficult to come up with analytic solutions. So it'd be nice to be able to do it numerically as well. So this is what Igor's really, Igor should have full credit for this. He's come up with this beautiful application of a master equation for open systems. The dynamics of the photon gas are contained in here. The magnetic spin system dynamics, the response, is contained in this integral. And this integral, in the quantum limit, this is the definition of the Green's function, the response function, which is a commutator of these spin operators in a rotating basis. And the nice thing is, we can work with this to some extent analytically, but we can also, by converting it to a semi-classical picture where we go from the commutators to Poisson operators, the Poisson brackets, I mean, then we can make a connection to something we can solve readily with existing numerical problems. They're called micromagnetics, which can integrate essentially those equations of motion I showed you before. So the picture is we've got some sort of driving, and it's going into this coupled photon cavity magnetic system, and we have a dynamics which is described by this master equation, and we can extract this bit, if we want to, by going to a semi-classical picture where we go from commutators to Poisson brackets, And we can then, in the Poisson brackets, numerically evaluate these derivatives. These angles just specify the orientation in a spherical coordinate system of the individual spins. We can do an average over these over time and extract all the information we need to calculate these equations of motion and hence predict the two modes, the stable and unstable modes. And so this is an example. We have these. We've done this for a single spin. We've done it numerically using micromagnetics. And we see indeed that the Poisson brackets give us the information we want. There's the, we have a center driving frequency here. There's a mode, which high frequency, a mode at low frequency. This mode at low frequency is the unstable mode. That would give us the effective negative energy if we were in the rotating frame of reference, and that would give us mode attraction. And so this is where we're at so far. So, oops, I think I've run over time a bit. We've talked about this phenomena of mode attraction and the creation of exceptional points in a simplest possible generic model, an optomechanical model. We've shown that this can be realized in certain systems of ferromagnets and even more complicated antiferromagnets and helical magnets. Then we've generalized this whole approach to talk about the inherent nonlinearities in the magnetic spin dynamics themselves and come up with a kinetic equation theory which is able to describe that, including mode attraction, and it can be put in a form, in a semi-classical form that connects to, makes it possible to study more complicated nonlinear dynamics numerically in a micromagnetic model. So thank you very much. Sorry, I ran over a little bit there.
No problem. Thank you very much, Robert. We have time maybe for one small question, if there is one small question. Otherwise, we can thank again Robert and